Good afternoon. Thanks, everybody, for joining this month's webinar. Today, we'll be featuring some great case studies on innovative water efficiency strategies focused on cooling towers, water reuse, water recycling. Moving towards increasing our local water supply is a huge priority, not just for the city, but for Southern California. The drought is not over, and there is not an end in sight, so we have to look at every potential source for water, every potential way that we can reuse and get the most beneficial use out of the water that we do have. A few housekeeping issues. As usual, the lines will be muted just to keep things orderly, but there, I hope, will be time for some questions at the end. We do have a lot of content today, so if we're not able to get to all of the questions, I apologize in advance. Please do email us or submit them through the question bar on the right-hand side of the screen, and we will be sure to get back to you. We're also recording the webinar as usual, and we'll be circulating that in a follow-up email as well as posting it to our website. And I talked about Q&A. Hopefully we'll have some time. We have some great guest speakers today. Maureen Urbesnik, our technical advisor, will be leading the discussion and asking some questions throughout, and we have some great guest presentations. So with that, I'll hand it over to Mo.
Thanks, Dave. Yes, we do have some fabulous speakers today just discussing some of the most innovative projects in the water efficiency market. We have Mark Gittleman from Rising, John Rowan from Capture H2O, and Mike Floyko from Dynamic Water Technologies. And starting up first, we have John Rowan. He's the founder and CEO of Capture H2O. And after 2 decades of working for several chemical and physical water treatment companies, John founded Capture H2O, and he did it with the explicit intention to provide commercial and industrial markets with a wide range of innovative water conservation treatment technologies. And they're always looking at new researching best water treatment and conservation technologies, and have designed some of the most sophisticated treatment systems, including for companies such as PepsiCo, Westfield Malls, Google, and United States military. I'm going to turn it over to John now.
Thanks, Mo, and good afternoon, everyone. Today I'm going to discuss efficient cooling water tower treatments with alternate water sources. I'll discuss a little bit about water treatment 101 and discuss traditional water treatment approaches and the challenges with those approaches, then get into CAP-R sustainable approach, and then discuss 2 case studies. So why do you treat cooling towers? The water in Southern California has a lot of minerals in it, corrosive materials, and the temperature of cooling water is such that it really grows bacteria and has a lot of food sources in it. So the reason why you need to treat cooling towers is to control scale corrosion and bacteria for energy efficiency, for asset preservation, and also for health and safety. Traditional water treatment, if you look at a building cooling system, you have your cooling towers, which are designed to evaporate water to reject the heat that you're removing from your HVAC equipment, like a chiller or a plate and frame heat exchanger. Water is recirculated through that system, and the minerals that are in that system are constantly concentrating up because you're evaporating off pure water. So these systems need to make up with fresh water constantly, and then also you'll have a controller that's attached that's sampling that water and determining the dissolved solids levels, and then you have a solenoid valve that needs to dump when the levels get too high. So a traditional water treatment system has makeup water, evaporation, and blowdown, and you also have to pump in scale corrosion and bacteria control chemicals. So there's a lot of moving parts and a lot of complexity to it, and a lot of water usage and water waste. So normally, what are the approaches that people take? From a water conservation standpoint, if you use straight city water, you can typically concentrate that water up between 2 and 4 cycles, which means, and LA has a new requirement where they want to see a minimum of 6 cycles. So a hard water program doesn't necessarily meet that. You have to pump a lot of chemicals in, and if there's a failure with the system, you get scale and bacteria growth. If you take that same chemistry and you would control the pH by adding acid, you can increase the cycles and reduce the water a bit, but it's still below the minimum. There's other programs that you use. You really lower the pH and use another chemistry. That takes you, you can cycle the water up even higher and get more water conservation, but you increase your risk of failures when you do that because of the pH control and the hazardness of acid. Finally, you could partially soften the water going to these cooling systems and meet or exceed the minimum of 6 cycles. So that's the traditional water treatment approaches. If you go to the next slide, I'll talk about why these systems have failures. The main reason is because they rely on blowdown control, water to be dumped back to the sewer, and there's where you have a lot of mechanical failures. Solenoids fail, makeup floats fail, your controllers require calibration. You need multiple chemicals. You have to maintain secondary containment, and you have to manage those chemicals by pumping them in. Number 3, and this is kind of a big one, is traditional water treatment doesn't necessarily it prevents scale from forming, but it doesn't remove existing deposits. And number 4 is these programs typically require very stable makeup water quality. So if you're using alternate water sources like rainwater or groundwater or recycled water or a blend of any, it makes the systems don't function or don't respond well to that changing water quality. So what does Capture H2O do? We shift the focus of the water treatment from the reliance on that blowdown control where you have to dump water and pump chemicals back in to relying on a pretreatment system to treat the water going into the cooling system. We create a system that's simple and it uses natural chemistry and is self-restorative, meaning it will remove existing deposits and it's very forgiving. This system also allows us to handle varying amounts of different water sources going to the system without having to make adjustments. We incorporate real-time performance monitoring and alarming of the key performance indicators. And finally, we support the system with a high level of technical service. So a typical installation would look like this. If you remember that slide earlier, how many more moving parts were on that and how much more, this is the basic system that we need to run this program. We install high efficiency pretreatment system on the cooling tower makeup, allowing us to remove the minerals, 100% of the minerals going to the cooling system. With that, we can operate the system. We do have blowdown controllers and other stuff that we put in here, mainly for performance monitoring, but this is the basis of what we would need. So how does it work? As I said earlier, we're trying to control scale corrosion and bacteria. Scale control comes from removing the minerals in that water. So whether it be groundwater, rainwater, or recycled water, or city water, the system removes all the scaling minerals before they get into the cooling towers. This allows us to remove the limits on how high you can concentrate that water, and we can run from any level of blowdown to zero blowdown if we wanted to. So scale control comes from removing the minerals in the water beforehand. Bacteria control comes from concentrating up that water so the pH rises to create a biostatic environment where bacteria can't survive in the water. Corrosion control comes from concentrating up the natural silica that's in the water. So the groundwater happens to have higher silica than city water in LA, So it's actually a very good fit. The higher silica, the better this program is. So ultimately, we're creating an environment where we're using the natural chemistry of the water. We just have to pre-treat it first before it gets in there. It simplifies the water treatment program, eliminates the failures associated with blowdown control, and of course we remotely monitor it so we can proactively manage the program and ensure that it continues to work. And it can be operated at any level of blowdown, up to 0 blowdown. So it gives the maximum water efficiency. So next I'll discuss 2 local case studies. So first is Westfield retail malls. We have Westfield malls all over the country, but here in LA we have the Century City Mall and we have the Topanga Canyon Mall. So before we implemented this program on these 22 cooling towers, they were operating at about 2.8 cycles of concentration and using 3 chemicals per tower. 2.8 cycles of concentration is roughly 35% of the water is blown back down to the sewer. They had 62 chemical feed stations and pumps, and they had inconsistent water treatment results, meaning they would, every couple of years or a different mall would have scale in their chillers or bacteria or high corrosion rates. So the results weren't steady and consistent. They were using 164 million gallons of potable water and dumping about 60 million gallons back to the sewer. After we installed our system, the Century City Mall is using rainwater and city water as makeup. Some of the other sites are using recycled water, air handler condensate. The Century City Mall is going to also has groundwater, so we're going to add that to that facility as well. But looking at the portfolio, we've eliminated about a little over 100 million gallons of potable water usage, eliminated 62 chemical feed stations, and provided very consistent water treatment results, meaning no scale, no biofilm. The corrosion rates of all the metals have gone down to world-class levels, and most of these sites have had rebates that help pay for the system up front from the water conservation, and typically have a very short payback, less than a year, just for the water and sewer savings. So this diagram here shows what we did at the Century City Mall. When they redid that mall, they built in one of the parking structures, there's a cistern that's below about 10 parking spaces that holds about 500,000 gallons of water. So the rainwater off the roof was diverted into that cistern, where we have ultrasonic level sensors that will, when that tank's full, it'll fill that tank first, and then it'll divert the rest to the storm drains. So the water comes into that cistern. We also have a city water backup. So say there's no rainwater, it'll make up automatically with city water. Comes out of that tank, goes. We repressurize it through some pumps. We go through a multimedia filter which removes suspended solids from that water. Then we go through the pre-treatment system, basically softening that water. Goes through a UV sterilizer, mainly for E. coli control of that rainwater, and into the cooling towers. Cooling towers, we have remote monitoring and such, and corrosion monitoring. So this is what that system looks like installed. The filter is on the right, softeners are on the left, and you can see the UV sterilizer there as well. Some pictures of the mall. So this graph shows the results of the remote monitoring. So the graph on the top right shows the pre-treatment system that's treating the water. This system is online 24/7, sends out alarms. Anyone who can access the internet can access and has a password can access the data. So the first graph shows the water softeners that we have installed. When they regenerate, that they're getting enough salt, so they consistently can produce soft water coming out. The graph to the upper right shows the water usage. You can see over this period of time, the water usage dropped, mainly because we created the environment where we're naturally getting water treatment by not blowing down the water. So the graph on the lower left shows the cooling tower conductivity and pH rising because you're not blowing down. And then the bottom right graph shows the corrosion rates of the steel and copper. And so if you can see that our corrosion rates for steel average 0.18 mils per year, which below 1 is considered world-class. So these are extremely low corrosion rates. And we're getting all of this without having to add chemicals, biocides, scale inhibitors. We just operate that system so we naturally get that water treatment without having to pump in a bunch of chemicals, and we use these alternate water sources to save the potable water. The next case study is Google Spruce Goose, which is in La Playa, just north of LAX. This is a new construction that converted the 1940s Spruce Goose hangar, where Howard Hughes built the Spruce Goose seaplane, into an office and data center. It was started up in January. When they designed the plant, they wanted a minimum of 15 cycles of concentration, meaning roughly about 7% blowdown is the most they wanted. And they wanted to be able to use at least 20% recycled water without having to use hazardous chemicals and liquid hazardous chemicals. This site secured some rebates from water conservation as well as LEED credits for using alternate water sources to the cooling system and reducing chemicals. So the pictures here on the left show the 1940s of the building, where the Spruce Goose hangar and the building, and the ones on the right show what it looks like today after they repurposed the building and built the inside of this. So currently they're using both potable and recycled water for cooling tower makeup. They're operating at 15 cycles, and we started to meet their minimum of 20% recycled water, but we're slowly increasing it to we're going to use 100% recycled water into that cooling system. After we haven't used any chemicals after the third month of operation. Typically these systems, to get the metals passivated and to get everything lined out, we feed a little bit of silica in the beginning to get the passivation chemistry on the metal. But after we have that, we can eliminate that chemical. So right now they're currently not using any chemicals. They have no chemical feed stations. There's no scaling in on any of the equipment. Bacteria levels are non-existent. The water is basically sterile, and the corrosion rates are really low. And again, they've gotten rebates and LEED credits for that project. This particular system is our skid-mounted version. Everything's in stainless steel. We had the system, the pumps, the control panel all pre-assembled, shipped in. To the right of this picture, there's a storage tank where the water blends in. But this system basically can handle up to 4 different water sources into that tank to the right, repressurize the water, go through the pre-treatment system, and send it into the cooling tower. So we can customize the ratio of the waters and such. So we're maximize the use of the free or the least expensive water, and minimizing any potable water usage. Picture here is where the new cooling towers went in. This was during the construction part, but this is across the parking structure from where that building, where the hangar is. But it supplies, chilled water down over into the main building. Again, this slide shows results from the program. You can see the pre-treatment system monitor graph up on the right-hand side. It shows water pressure when the system regenerates, shows a curve. Our water consumption is on the right. our tower lower left shows the tower conductivity rising as we were eliminated the blowdown. And then the bottom right shows the corrosion rates for the steel and copper. Our steel is less than 1 mil per year, and our copper is almost 0 at this point. So in summary, this is an excellent sustainable technology that reduces water, chemical, energy, increases the equipment life, reduces the risks of failures related to water treatment, produces consistent, reliable, and repeatable water treatment results. And really probably from this conversation or this webinar, allows us to use alternate water sources, including groundwater, recycled water, rainwater. We have clients that are using wastewater that we pre-treat. All of this system is very forgiving to varying blends of water without having to add complexity to the water treatment.
Thanks, John. That was really interesting, and I think right in line with the goals of the city of using alternative sources. I'll hold off on any of my questions till the end. It's about 12:20 right now, and we'll move on to Mike Boyko from Dynamic Water Technologies. Mike is a principal at Dynamic Water, which is an innovative electrochemical water treatment system, which improves water, energy efficiency, minimizes maintenance, and eliminates the need for chemicals. Mike is going to go a lot more into the technology, but he's been working in pollution control technology since 1991 and really has a strong commitment to the economical, environmental, sustainability technologies, and it's what brought him to this UET technology he's going to discuss and forming Dynamic Water. He was researching a project for a customer or client a few years back who had a really challenging process water treatment issue, and it led him to UET, which is an invention out of Israel. And after much diligent research, Mike validated the technology and formed Dynamic Water Technologies, acquiring the rights for UET in North America. Since then, they've had much success with installations at NASA, Roche Pharmaceuticals, Banner Health, Dignity Health, saving millions of gallons. And turn it over to you, Mike.
All right, thanks, Maureen. I appreciate it. Yeah, as she said, I've been in pollution control systems basically my whole career, focusing on a lot of heavy industrial sites, manufacturers, cold storage facilities. And I started focusing all my time and energy on water and wastewater treatment processes. So we have two primary technologies. I'll only go into the primary one, which is universal environmental technologies. Go to the next slide, please. So I'm going to talk about a case study. Again, this technology, we acquired the rights at the end of 2015. And so the beginning of 2016, we started marketing the technology. And I entered into a program with the General Services Administration and the Department of Energy. We did a study over 2016-17 on a project in Georgia, had fantastic results. And then we were talking with multiple other groups, and one of them happened to be the city of Los Angeles. And when we got into discussions, they said that they had an active interest in trying to conserve water. And so we took a look at some of their properties, and they told us that the Los Angeles City Hall East building was of particular interest for them. This is actually houses the data center for the city of Los Angeles. And Michael Samuelin showed a particular interest and said, this is the building that he would really he would like to focus on. Maureen actually helped us along and said, the LABBC also has an active interest in this particular property. And so we started going through the property, investigated the application, how many cycles they were currently running. During the process, I started looking at what I wanted to prove throughout the study part of this process. And since I had worked with the National Renewable Energy Laboratories through our Green Proving Ground testing for the GSA, I asked Michael DeRue from NREL to monitor and record the findings. And so he had agreed to actually do a baseline run before our system actually started. And then we started our system actively in April 22nd of this year. That was the active baseline. We actually went live with our system on July 7th. Next slide, please. This is just a general layout of the process. We installed 2 skid reactors. These are side stream reactors using an electrochemical process. And so what we're able to do is take the makeup water coming into the process, pull it into our reactors, pull out unstable mineralization, as well as sanitize the process water, generate chlorine and hypochlorous acid from the chlorides in the water, and go back into the basin. Next slide, please. In this image, you can actually see one of our reactor skids installed between 2 of the towers. And then, like Capture H2O, we use a real-time monitoring process where we get 24/7, 365 monitoring of all of the particular parameters, the pH, ORP, conductivity, corrosion rates, so that we have active understanding of what the water chemistry is doing. We can also do a lot of predictivity, or basically predictions of how the water is trending. And so as we've seen the drought continue, we've actually seen quite a change in the water quality. Our system does react and adjust according to the resistivity of the water. So as conductivity varies, our reactor actually has a PLC controller that will change according to that modification of the water pH and conductivity. Next slide, please. Inside the reactor, we're actually pulling unstable mineralization. So we're leaving the majority of the calcium, magnesium, and silica because we agree that is a great passivator, but also preventer of corrosion, provided it's in a stable state. So by leaving the majority of those elements, we basically accelerate the scale formation that nature wants to deliver inside our reactors by creating a pH gradient from 0 to 14. We have a titanium anode in the center of our reactors, and what this does is it allows for a low pH of around 0 with a high pH on the cathode wall of around 14. And this basically directs the mineralization that wants to scale to form scale very quickly, about 1,000 to 1,500 times faster than nature would normally form it. What this allows us to do is take that unstable mineralization out of the water, and then the remaining water is actually in a very stable state, what we call a dynamic equilibrium, which is basically, everyone wants to reference the Langolier saturation index, or the natural scaling of water and the mineralization that it has. We're actually shifting that, and so we're operating at a very high pH range, usually around 8.7 to 8.9, and we hold it in that range. We're running, I believe, LA City Hall approximately 10 to 12 cycles right now. And again, this is without having to add any acids, inhibitors, or related materials in that anti-corrosion or anti-scaling. We don't require those. This material was formed in about 3 months, and we usually go in the first 1 to 2 cleanings manually removing it so we can do a mass balance and double check how much mineralization we're pulling from the water versus what we calculated in our water testing. And we keep that in balance. Once we've established the baseline parameters, our system is pretty much plug and play and runs very well. We do an inspection once a month, double checking everything, and then the site will do water chemistry several times a week just to see that the water chemistry is staying in compliance. The nice thing is we are also generating chlorine and hypochlorous acid, which is measurable, so that according to CTI standards, we can achieve basically the regulations that most people are observing. Next slide, please. This is, again, just a quick cutaway or overview of what we're doing. So we're putting low voltage DC current. We take 110 volt single phase into our power transformer, convert that to DC current, and we're using a maximum of 16 amps DC to create partial electrolysis in our system. And so as I said on the prior slides, we're doing 2 things. We're guiding the mineralization, the calcium, magnesium, and silica, to layer out if it's unstable, and the remaining calcium is basically balanced in the process. And then we're also converting the Cl3 into Cl2 minus and HOCl. So we're generating hypochlorous acid and chlorine naturally from the water. Next slide, please. We also actively checking dip slides, and so we're monitoring any kind of biologic growth. We've had excellent biologic results from the process. You can have up to 10,000 coliform units per milliliter in most cooling towers in the United States, although New York State has actually changed to 1,000. Our processes are typically well under 100 and always under 1,000 CFU. This is just a little reference if you're not familiar with dip slide results, but we'd like to do this once a month just to double check. Next slide, please. As I mentioned, so NROL is actually monitoring the process for us. Michael DeRue is a PhD researcher for the Department of Energy out of Colorado and was brought in early on. Next slide. He's been monitoring a number of different elements in the process. And so when we started the baseline analysis, the initial set point the chemical water treatment company had set, they had some variability. They were at 3,400 and then had dropped it to 2,400. We believe that was due to the increasing mineralization of the water, but we're not exactly sure why they chose to drop that cycle rate. It was quite interesting. So since we've started our process, we had an initial set point of 5,500. Actually, we've just raised it to 6,000. We usually push anywhere from 7 to 8,500 microsiemens conductivity. And this, again, was without any kind of additions of acids, corrosion inhibitors, or scale inhibitors. The first 2 months, we actually showed a net savings of about 250,000 gallons in the process. Next slide, please. So they're doing a very, very careful measurement process. NROL, we're not dictating how they do it. This is up to them. They put in several different devices for monitoring, as well as working with JCI and the City of LA. They are doing several different models that are adjusted according to the demand, the building demand, the weather, the dew point, and they're showing anywhere between 15 to 19% overall water savings for the process at this point. Next slide, please. I want to just mention, the drought conditions that we have seen in California are ongoing, and I have been looking at quite interesting trends that we're seeing in this process. If you go to the next slide, since we started our analysis of the building and gone through, this is actually a graph of the conductivity that we've recorded in the process, and as you see, it's had a dramatic upswing. It seems that it's continuing on this path, and past this point, we're seeing some dramatic fluctuations that are quite unusual. I don't know for certain that this is a direct indication of instability in the makeup water, but we've seen that in other markets where once you reach a certain saturation point, you get dramatic instability in some of the silica and other and the overall hardness of the water. Next slide. And of course, I regularly look at the U.S. Drought Monitor. Every Thursday they come out with updates. And this is just a little reflection. You know, from 2012 to 2016, California experienced an unprecedented drought. In 2017, they had a reprieve from this. They had some rains, and it helped. But if you look at what's happened now in September of 2018, you're back in that drought, and it is progressively degrading. So there's things that we have to take a look at very seriously. And unfortunately, as water conditions get worse, usually people are ramping their cycles down, which means they're using more water. So unfortunately, it's counterintuitive to what we're trying to do as far as water conservation. So next slide, please. And again, if anyone has questions, I'm more than happy to answer anything or do any analysis that you might need on water conditions.
Thanks, Mike. That's really interesting part about the water quality, just how it differs during all of the sources, droughts, where you're located in the city.
Yes.
And just as a note to everybody, we are working with NROL on the case study, and within the next month, we'll have detailed information on water savings, energy savings, maintenance, chemical, and we'll share a case study with the group on the call. And now we'll go on to Mark Gittleman. Mark oversees third-party services throughout Rising's 3 million plus square feet of commercial real estate. And he also does business development of integrated verticals and Rising's technology initiatives. He has participated as a GP investor in over $600 million worth of transaction and is co-founder of 5x5 Telecom, a commercial real estate-focused internet service provider. Mark is a noted expert in real estate innovation and his creative leadership has led to advanced technologies throughout Rising's portfolio and has garnered national attention for Rising, and they are recognized as one of the most innovative developers in Los Angeles. And Mark's going to talk about a case study at their 1200 West 7th property.
Thank you for the intro. As an update, I we promoted Casey Hawk into the operational role, and I've taken a senior advisor position on technology. So my role at Rising is purely focused on technology and innovation within the company, which we're going to talk about here. So just before I talk about this specifically, the two gentlemen who just spoke, like most of what I know about water treatment, I learned from one of them. And this project was actually brought to us by Maureen and Dave when we were going through the acquisitions process for 1200 West 7th, the Garland Center. So for those of you who don't know, 1200 West 7th Garland Center was built by First Interstate Bank. It's actually the only purpose-built data center in Los Angeles. There's about 250,000 square feet of subterranean data center with more infrastructure that is far beyond anything else in the city. It's about 500,000 square foot office development above it, and there is also a development parcel. So it was a really interesting project. And as we were going through the due diligence, as I said, the three people that are on the call here, Dave and Maureen and John, actually came to meet with me to talk about John's product, Capture H2O, which I'm a huge advocate for both of these. I have not been able to convince the asset managers within Rising to pull the trigger on one of them yet, but if you want to learn about water treatment and like how this stuff works, they're phenomenal resources. So that slide wasn't in here, but if you just advance forward, please. What we learned in this process is that there's a spring under the building that we were sumping water out, and it was, $24,000 to $36,000 a year that we were paying to discharge the water. And we were sitting in a conference room in my office, and John said, well, the water's clean. Like you can drink it. We tested it because John had put together a proposal for the prior owner, and they never just went forward with the project. So if you fast forward here, next slide, please. Thank you. So before I go through the bullet points on this slide, the whole idea of talking about this is the internal approach to found a very, very simple solution with people who were inclined to just point us in the right direction, and found a very elegant solution that cost us very, very little to implement, but resulted in a huge savings. And we're going to talk about that in a second. So the process, and we'll show some photos here in a second, was we installed a Y pipe and a bunch of plumbing and diverted the water that we were paying to dump into the sewer into a storage tank that now fills cooling towers. It doesn't provide 100% of the water, but you'll see in a second here how much demand we were able to reduce. We just saw some slides relating to drought. When you start talking about saving upwards or more than 1 million gallons of water a year by basically installing a pipe, it seemed like a very, very sensible thing to do. So if we go on to the next slide, please. So our savings is approximately 1.2 million gallons a year. Whenever I do statistics, it's very hard. I guess there's probably two people on this call that can picture what 1.2 million looks like in gallons, but for people who can't, that's literally taking a shower for like 6 lifetimes. So it is a phenomenal amount of water. And when we think about the city and the shortage of water, it made sense from a socially responsible corporate citizen perspective to do this, despite the fact that it costs very little to do it. So we reduced our LADWP water bill by about $20,000 a year. We reduced our sewer charge by about $30,000 a year. And so far we've saved about 2.5 million gallons. And the funny part about that statistic is the most expensive part of this was we have a phenomenal chief engineer. His name's John Barco. I said, John, this is really cool. You've estimated what's coming out of this pump. I said, I want a meter that goes back to the BMS. So when we're walking through here with people in the engineering plant, we can point to a screen that shows savings. So, getting the meter installed and the cabling and then programming the BMS to read it was actually the most costly part of this whole project. So if you go forward onto the next slide, please. So that, again, is what we did. It was very simple. I actually thought we had some images in here, but it looks like they didn't make it in here. Essentially, the installation, we put in a Y pipe. One Y was going to the sewer. And We put in a Y pipe, we plumbed it over to a storage tank, and we draw water off of that to fill the cooling tower. And again, it should reinforce that with the right perspective on property operations and asset management, combined with the resources that the people who put this webinar together are in the city charged by the utility companies, frankly, to provide, are phenomenal resources. And without them, we would never have even known this existed and known how simple it was for us to do. So that's everything I have to say. I'm happy to take any questions relating to this or the general topic.
Thanks, Mark. So simple, but so sophisticated. Yeah, that's really great information. I think that what we're learning here today is that cooling towers are a top opportunity for water savings, that there are some really innovative technologies available in the market, both chemical and non-chemical, but the solution's got to be site-specific, depending upon the water quality and the company's needs and return on investment requirements. That using existing groundwater, like Mark did, that discharge can be easy, and whether or not it's groundwater use, cooling tower, water treatment, it's worth assessing your property, and we're here to help. So you have our contact information there, and then I think we'll start fielding some questions. So, Mark, question for you.
Yes.
How much did the project cost you?
That's a good question. I don't know the specific number. It was so little that I never looked at it. Like it didn't come across as any variance in the operating expense or maintenance of the property. I think it was literally it was rounding error.
Did you install the equipment yourself with like internal staff, or did your vendor do it?
Internal staff, yes, good question.
Okay.
So John had the materials on site, and him and his team plumbed it. Acquired some of the materials, obviously the meter that we discussed and the Y pipe. It's a data center, so there's lots of plumbing, right? There's lots of plumbing capacity and lots of parts laying around. So they were able to utilize parts that were on site and put it together, and it was literally as simple as that. I'm not overemphasizing how simple it was. It was like a complete no-brainer. It's one of those things that you look at and you're like, that's so silly that it wasn't done before.
That's
but
great.
again,
no,
if we didn't
no
have
special water treatment.
No,
you didn't have to change that.
But if we didn't have you guys introducing us to John in this case, and literally like John said it in passing in a meeting. He's like, "Oh, you guys can still just use the water." Like if it wasn't that the relationship with you guys and setting it up, we would never have known. But it was such a simple thing, and I think that we had, for those of you on the call, obviously when we do these, we have prep calls in advance, and Marina and I were talking, and I said, in a project like this, we can never, quote, compete with something like what Cedars did. But what Cedars did was a phenomenal project, and it took a small army and construction management, and I mean, there's a huge budget to do it, and it's a phenomenal savings. But what I wanted to emphasize was that just by looking at problems differently, or just talking to people who look at problems differently, there's an opportunity out there to probably do lots of projects like this that are super low bar to achieve. But when you add them up and you take a look at this scary map that we just saw about the drought, can really make an impact in not just how you operate your property and the image of your company as being green, but in how water is consumed in Southern California.
Yes, very true. So, John, can you tell us a little bit more about what an implementation looks like in regards to process and time? Like, how long did it take at Westfield or Google to make those projects happen?
Very, very quickly. Typically, the to size a system is, a couple hours on site doing a survey. Then we put the equipment together, and installation is typically 2 to 3 days. It all depends on how complicated the project is. Like, if you have to move water usually you're moving water from one area to another when you're talking about groundwater. Like Mark just said, that facility at the Garland Center is pretty, relatively close to where the groundwater was, where it has to go. Whereas some of the projects, if you have groundwater that's down in, the parking level 10 or something like that, and you have to get it up to the ground floor to where the tower is, that could be a little longer. But the Westfield and the Google projects are all ground floor, so it was really easy to implement, and it's really not invasive to if you're retrofitting an existing site.
So as follow-up to that, are there any permitting issues that you would have on those? Do they require special permits?
Not the projects that we have. It's more of just making sure that you're meeting, like if you're using rainwater, for example, you have to do some sort of sterilization of that water while it's being used. But the groundwater part, no.
Really interesting. Great. And Mike Boyko, what is the city going to do once the final results are in? What are they going to do with the project?
So what we've seen right now, the city has a number of buildings with an active interest in making some improvements. We're going through a number of them, just trying to identify where the greatest opportunities are for savings. Some facilities, like the library, is very well run and has a high cycle rate. And so what we're trying to do is identify the buildings that they may have had more challenges, or they have older equipment, or for whatever reason they're running a lower cycle rate. And by making the difference between, say, 2.5 to 3 cycle, getting it up to 10, 12 cycle range, we've saved the majority of the water people can save. Once you get past about 10, 12 cycles, that's about the curve goes very flat, and so your net water savings is very small. We think that getting into the 10, 12 cycle range is really the goal people should be shooting for in order to justify that. So the city has basically shared with us that there's a list of their target buildings. Here's the ones that may represent the best opportunity for water savings, and we do a site survey similarly to what John was commenting on. Once we test the water, both the makeup and the basin water, get an idea of where they're currently operating, we can generate a proposal and size our equipment accordingly. And so we should be presenting several other proposals on other buildings for the city over the next 30 to 60 days.
Interesting. So when you're looking at a target size, is it a cooling tower size or the cycles of concentration?
Both.
Okay.
Yeah, both we want to look at. There's definitely diminishing returns. If you have high cycles already and you had a small tower, it's probably minimal savings. If you have larger the tower, the better the general opportunity is, and the lower the cycle rate, again, the better the opportunity is for overall water savings. We typically like to start looking at facilities with towers, I'd say in excess of, say, 200 or 300 tons. Unless there's multiples on the site. I have a couple of customers that have many towers on their property, like a NASA, for example. They have several large towers, but then they had, I think, 4 relatively small towers. But because we're on site, we're still doing a project to treat those processes.
And what's a general rule of thumb for the cycles of when you should be looking at?
I would say if you're under 6 cycles, we would definitely want to start looking. What we see here, in both in California and in the Southwest in general, most people are running somewhere in the 2 to 4 cycle range. Very seldomly do we see a lot of chemical treatment systems that are running in the 5, 6, 7 cycle range. Occasionally we come across it, but I'd say 75 to 80% of the systems are running below 4 cycles.
Great. Thank you.
Mm-hmm.